Hey guys, so this is section 6.7, the equilibrium constant for a mixture of gases, introducing it. Alright, so let's start with our generic chemical equation, AA plus BB and so on. And we're going to say they're all ideal gases and the total pressure is 1 bar. So we developed earlier that the partial of G with respect to the extent constant P and T is equal to the sum of the coefficients times the chemical potentials of the species, which is equal to products minus reactants, coefficients times the chemical potential under standard conditions plus RT ln, or the ratio of the partial pressure of that species to 1 bar. And so we developed this equation earlier, now let's use it. So first thing is, at equilibrium, we know that partial G with respect to extent is equal to 0. We saw that before, which means if we go back over here, guys, whoops, not there, here, set this whole thing equal to 0, pull out the, distribute the coefficients inside, pull all of the chemical potentials over to one side, set it equal to 0, pull them to one side, the natural logs on the other side. We end up with this right here. This term over here with all the chemical potentials, it's the products minus the reactants, each times their coefficients. That's just delta U, mu, delta change in chemical potential under standard conditions. This, we can use some properties of logs. For example, x times the natural log of a is equal to natural log of a to the x, and also natural log of a plus natural log of b is equal to natural log of a times b. Using those properties, we can rewrite this side of the equation like this. Pull out the RT, the negative RT. Then we're going to have natural log of, this is the ratio of the partial pressures of the products raised to the power of their coefficients to 1 bar over the reactants in the same way. So at equilibrium, we know that delta U, mu, the change in chemical potential, is equal to negative RT natural log of this ratio, where this is delta mu. That's equal to the sum of the coefficients for each species times the delta G of formation under standard conditions of each species, because we saw earlier that the chemical potential under standard conditions is equal to the delta G of formation under standard conditions. We have a name for this ratio right here, the term that was inside of the natural log. It's called the reaction quotient at Q sub P. So with that in mind, using that, now we can say partial G with respect to extent is equal to the sum of the coefficients times the chemical potentials, which is equal to delta chemical potential under standard conditions plus all these natural log terms, products minus reactants. If we collect the natural log terms here, and we can, basically we can write it as natural log of Q sub P. We get this very useful equation right here. It says partial G with respect to extent, constant pressure and temperature, is equal to delta G under standard conditions, which is a function of temperature only, plus RT, natural log of the reaction quotient. Real useful equation. Notice that we have broken down the dependence of partial G with respect to extent into a term that depends only on temperature, delta G under standard conditions, and a term that depends upon partial pressures of the products and reactants only. That's what Q sub P does. It depends only on the partial pressures. So looking at this equation, we know that when this system is at equilibrium, partial G with respect to extent is equal to 0, which means that this term here is equal to negative this term here, or that. When we're at equilibrium, we have a special name for Q sub P, the reaction quotient, and it's the equilibrium constant, K sub P. Now, Q sub P, it can have, even at the same temperature, it can have all kinds of different values. Whatever the partial pressures of the products and reactants are raised to their powers, gives you a Q sub P. K sub P is always the same. It's a constant at a given temperature. It does depend upon temperature. We'll see that in a minute. Rearranging that equation, we get negative delta G under standard conditions, which is a function of temperature over RT is equal to natural log of K sub P. This side right here, everything depends only upon T, the temperature. That means that this term right here must also only depend upon temperature, which means that K sub P is a function of temperature only. So the equilibrium constant is a constant at a given temperature. We can also tell a couple things by looking at the form of this equation. Remember, Q sub P can have different values depending upon what the pressures are, partial pressures are. If, remember, it's products C and D over the reactants A and B. If the partial pressures of C and D are large and the partial pressures of A and B are small, so that the value of this, Q sub P, is larger than K sub P, the equilibrium constant, that means that this term right here will be, first of all, positive because the numerator is greater than the denominator, natural log of a number greater than 1 is positive, and it's also going to be larger than this term, which means that this whole term will be positive, and that means partial G with respect to extent is positive, greater than 0, and that tells you that if that's the case, Q sub P is greater than K sub P, the reaction is non-spontaneous in the direction written. Of course, it will be spontaneous in the opposite direction. So let's do an example. We want to calculate the change in chemical potential of the reaction for the same reaction that we looked at last section, this one right here. So what we did last time was we calculated the change in chemical potential at 298.15. Now we want to find what it is at 559 K. To do that, we're going to reach back into section 6.3 and use this equation right here. So we derived this back then, go look that up. And we're also going to use the fact that we now know that delta G is equal to the delta chemical potential, delta mu. So multiplying through by T sub F, we get this form of the equation right here. We calculated this right here in that last example. I think it was negative 8.3 kilojoules per mole, something like that. We know the temperatures. The only thing we don't know yet is the delta H of reaction. Remember, when we derived this equation up here, guys, we assumed that the change in enthalpy was independent of temperature over the different, the range of temperature between these two. So we're still assuming that. But we need delta H, but that's easy. All we do is we go look up in a table, there's one in the back of your textbook, the heats of formation of everything in that reaction. Well, heat of formation of ammonia ends up as negative 45.9 kilojoules per mole. These are just elements in their elemental form, so delta H of formation of both these is 0. It makes it easy. We have to multiply by the coefficients, so 2 here. 2 times negative 45.9 gives us negative 91.8. Plugging into that equation, remember this number right here, where it came from is we calculated this in that last example in the last section. Plugging in, please check my calculations, but I think I get 64.7 or so kilojoules per mole. The thing about that is that's a positive number, which tells us that partial G with respect to extent is positive, and that means that this reaction at this temperature will not be spontaneous in the direction written, but the opposite direction.